Okay, so the first question is from Adrian.
Yeah. Thank you all for the panels. It's great. My question is partly for Yossi, but maybe for Mike or everyone. So, my understanding is Richard Feynman wrote a paper on negative probability. And so, I mean, we know from the standard Kolmogorov axioms that probability is bound between 0 and 1. And I'm curious why Feynman wrote this paper. What was his conceptual motivation? And what ontological significance does this have if there are negative probabilities?
Suppose one of the way, of understanding negative probability is in terms of backward causation. And one can have an interpretation, it was Feynman and Wheeler that used, they had an interpretation for classical, actually, electromagnetic theory that had, causation in both directions. And in quantum, you can have theories, well, Frank also can talk about this. You can have a theory that is local, or in principle could be local, and then more easily reconciled with relativity theory. In my view, I don't understand what negative probability are, because I think that probability theory historically always started as a philosophical, from philosophical ideas. Actually, Kolmogorov, in a way, is one of the exception and his influence. But if you look at the history from the 16th, 17th century, it was always philosophical, and even before they had a clear formalism. And also in the 20th century, people like Frank Ramsey, like Keynes, or De Finetti that I mentioned, a number of them, they always started from the philosophy and then got to the formalism. So philosophically speaking, negative probability, I don't know what it means, in terms of possibility. You have negative possibilities. It's kind of, for me, it doesn't make sense. But in kind of fairness, I know that some philosophers do actually follow that and are interested in that. For me, it's just a formal thing. In quantum mechanics, if we talk about probability, for instance, one can think about quantum mechanics as probability theory. And one way to think about, usually probability is based on logic. So classical probability theory is based on classical logic. It's the operation of classical logic produced this structure. And in quantum mechanics, one can think about quantum logic. So one can think about, let's say, von Neumann and Birkhoff, actually proposed, and the idea was that you give up the distributive law. So if I say, for instance, in classical physics that the ball is round and it's either black or white, we understand in classical physics it's round and black or it's round and white. In quantum mechanics, they propose that this is actually doesn't obtain. I understand it as a mathematical operation or like algebraic operation. I find it very difficult to understand it as a logic. So it's the same with probability. I think that it would be very difficult to find a logic that would support such a theory of probability. But one can say, we don't want to follow the tradition and think about probability in philosophical terms. Because one can think about probability as a measure theory. So, like the distance between here and here has the same axioms. Could have the same axioms as probability. But I think one loses something very important about probability, the expectation, all the connotation that we attach to it.
We're good? Okay, Ryan?
So my question is actually more asking about broad predictive abilities based on what was said on the panel. Dr. Steinberg, you mentioned that recently we've reached the point where, for the first time, fundamentals of the science are really relevant to the technological developments coming out of it and its applications. And I wanted to see from the panel, do you see the 21st century as differing from the 19th and 20th in the sense that it's less like an entrepreneurial, random technology developed and the science helps improve it, and more very tightly knit relationship between the philosophy and the fundamental understanding of the science? and developing some application of it?
Well, so there are always different approaches and takes toward technological developments. So there are highly scientific, mathematical approach toward technological developments, and you can see the sort of gems or combinations of this kind of work in the highly institutionally organized research laboratories like university laboratories or MIT or IBM, Bell Labs, you name it. On the other hand, there are some, another extreme is the down to the earth, sort of improvisational technological development that relies a lot on the experiences and tacit knowledge and a lot of technical know-hows without having to resort to scientific theories. So that has been going on since perhaps the establishments of modern research laboratory in modern sense, or even can trace back a little bit further to like the teaching laboratories in 19th century Germany, in which we have began to have more scientific industries. But I think the two trains and any kind of combinations in between still continue to live to these days. And I don't see that the major technical developments in our society have become converged toward more scientific sides of the developments. I think there are still a lot of things going on. Well, of course, if you want to really try a breakthrough, for example, you want to resolve the energy crisis, you want to increase the life of battery, you want to get yourself on the surface of Mars. So all these are tasks that require hard technologies, and quantum information, the foundation of quantum mechanics may provide some resources for us to solve those hard technical problems. But on the other hand, there are a lot of different degrees of technical problems that rely on different kinds of expertise. Science is just one of them. So that's my take of it.
Yeah, I would maybe, I wouldn't accept with such enthusiasm the impact of sort of this deep thinking about quantum mechanics on technology. I mean, it's certainly true that in the first experiments where people talked about, they used Bell's inequalities as a way to get to things like QKD or teleportation. Some of these earlier proposals were motivated by, sort of people struggling with fundamental issues in quantum mechanics that led them to these novel things you could do. But if you look at any textbook today on, quantum networks or quantum information processing or anything like that, you will find no discussion of interpretational issues in quantum mechanics. You'll find rules for POVMs and sort of completely positive maps and things like that. And you can go about and make the calculations and make your business. You can do your job doing that without thinking about these philosophical issues. So I'm not sure. I mean, it would be wonderful if I'm wrong, but I'm not sure these deep issues, besides, sort of the initial role they played in getting this quantum information processing field started, I'm not sure they continue to play an important role in the actual engineering development that's now happening in these areas.
So just very quick follow-up on this. So if you say go to a talk on like quantum computing today, I mean, in the first probably 5 to 10 minutes, the speaker will talk about EPR, Bell inequality, things like that, these foundation issues. But then the rest of the talk is going to be about like the material properties of the topological substances, or how do you dope the semiconductors in this or that ingredient to make this happen, or how do you tune your laser in this way or that way to create a kind of entangled states. So these are very technical and down to the earth considerations. And the roles, I would say, or at least the PR roles of the roles of these foundation discussions for the majority of this kind of thing is pretty much PR purpose from my perspective.
Yeah, I mean, I suppose as a philosopher, what bothers me is that historically technology and science went together. And technology was always very important, I mean, in development of science. And many times it was the same person who did the experiment who also had the theory. If you look at the philosophy of science community, there are very few philosophers of technology that are looking actually at how much technology influence science. And that's, for me, it's something that is really wanting. I think that one has to take, people now, philosophers of science look more into technology and look more into doing things and the issue of the experimental part that is important. I mean, and not just the theory, the abstract theory, because the abstract theory is only part of it. I mean, you can say more about it, but in my view, I mean, a lot of the experiments in quantum mechanics use pseudo-quantum mechanics. They don't really use quantum mechanics because it's extremely difficult to use it. It's a kind of pseudo-classical with something with quantum mechanics. And I was one, I mean, I was kind of commissioned to write something about philosophy of a certain subject, and there was experimentalist who did also theory, and he talked there, and I couldn't understand, I mean, what he was saying. And I felt really like, like an idiot. I mean, and then I realized, I said, well, you're not consistent with using the theory. And this scientist, I mean, was kind of smiled, not even, I mean, apologizing, says that, we go from the classical to the quantum very easily. We just put the hat, it's like to have a operator, and you just move them around and go back and forth. And it's not that, it's not that I'm kind of accusing the person. I think it's extremely difficult actually to use the theory. And many times we talk about the theory as if it describes everything, and we know it's just a problem, I mean, of kind of applying it or something like that. But I think a lot of the information and the evidence that we have about the theory is actually with models that are half-baked. I mean, classical and quantum, no?
Yeah, I'll say approximate. I'll say we like approximations.
Okay. Different degrees of approximation. Yeah.
Anyway.
Okay, Eddie?
Hi, I was wondering for the panel, can you guys hear me?
A little bit.
Speak up a little bit louder.
I have a quiet voice, so I shout. How? I was wondering if the panel or the field of quantum mechanics in general has a sort of position on Karen Barrett and the School of Feminist Scientists' view of quantum mechanics insofar as they integrate questions of ethics, and specifically a sort of politicized ethics, into what seems to dominate the field right now, which is questions of metaphysics and epistemology. I'm not sure. Are any of you guys familiar with it? It's super big in the humanities. We're always like, there, entanglement. This is the hot stuff.
I missed a word that you used before. You talked about this feminist school. There was a specific name to the school, or specific researchers, or
Karen Barrett.
Karen Barrett.
Okay, no, I don't know the name, and I don't want to speak for others, but I'll say as soon as anyone talks about incorporating ethics into quantum mechanics, I become extremely skeptical. I don't see any connection whatsoever between the two fields. And although I'm always happy if more people learn about physics and try to use what they learn in other places. When I hear that in English departments the word entanglement has become popular, my first guess is that it's being used entirely wrong. I think there are lots of cases scientific words can be used as powerful analogies, and it's really important to understand when they're nothing more than analogies. And we run into danger when people use the scientific concepts, translate them to a regime where they have no validity, and imagine that the conclusions that work in science are also going to apply to the humanistic, let's say, application.
Oh, I just add that quantum mechanics has been especially used for these sorts of purposes. And so that's partly true because quantum mechanics, even when we attempt with scientifically to approach the world in a completely scientific mindset, it turns out that the theory is quite strange. It doesn't behave the way that theories previously behaved. It is weird. It's not the title of this event is not a misnomer. But when that weirdness percolates up, it can be. I have no familiarity with the view in question, and so don't construe me as attributing this to this particular the school of thought. But there are instances where quantum mechanics has been used for purposes other, for motivating purposes other than completely scientific approaches to investigating the world, and that's in large measure because of the weird features that it has.
So I just want to add on that. So Mike is absolutely right. Quantum mechanics has been a source of imaginations or aspiration for the people outside the physics communities. In the 60s, 70s, and 80s, there were, some were alternative physicists who believed that they should pursue alternative careers. Some were members of the counterculture communities who believed that quantum physics sort of alluded to ways to think about things like ESP or psychological or psychic mind states of mind. So that has been quite a prominent, I would say American, probably not restricted to American phenomenon. Of course we can say that this is totally abuse of the quantum mechanics in the sense, it's a total misinterpretations of quantum mechanics. But on the other hand, this is an interesting cultural phenomenon which reminds us that this is indeed very strange and weird phenomenon, so that we cannot stop people's aspiration and imagination from thinking it and using it as something else. So I would say that it's interesting to observe this as a cultural phenomenon.
It's interesting, actually. I met someone years ago that was interested in the interpretation of quantum mechanics, and I wasn't sure why. And then it turns out that David Bohm, who proposed the Bohmian mechanics as an interpretation of quantum mechanics, he wrote about implicate order, which is related, I suppose, to entanglement and holism. And actually, there are clubs on the web that follow, that meet and talk about these things. So obviously, it had influence. And in this case, interesting, it started from the physicist. I think David Bohm, was a great physicist. But he had his views.
Greg?
Okay, so this is a question maybe for any of you, but maybe Dr. Miller could speak to it. You spoke to it a little bit. So here we are 100 years after this whole quantum revolution exploded, and almost 100 years before formalism was developed. And still, it's weird. And so, Dr. Miller, you gave some helpful suggestions that maybe actually appealing to not the theories that were developed in the 20s, but, quantum field theory or more recent theories might help us get a handle on what's actually going on. And one might say even that we need a theory of quantum gravity before we can really understand what's going on physics by itself. And so that seems appealing, but then on the other hand, it seems like, maybe if we don't know what's going on for basics, we should go back to the basics. And so it seems like there's kind of like, reasons that you might want to look at the more recent things and reasons why you might want to go back to square one, 1920 and try to approach it from that angle. So I'm curious of your thoughts on that.
Yeah, so I guess the first thing to say is that sometimes one hears optimistically that if we just learned what quantum field theory really is, there's questions about mathematically how to express quantum field theory. If we just learn what a correct theory of quantum gravity is, then these foundational issues are going to get resolved. And I guess what I'd say to that is that I don't see any reason to believe that. I see really compelling reasons to believe that all of these fundamental interpretational difficulties at the foundations of quantum mechanics are going to be preserved. They're certainly preserved when we move to quantum field theory. Unifying special relativity and quantum mechanics doesn't at all help you to resolve the measurement problem. In fact, as I alluded to earlier, it puts really significant constraints on the kinds of solutions to the measurement problem that we have in the non-relativistic context. So I guess the other side of this is that there has been, I'd say in the last 20 years, or maybe even just 10 years, some return amongst people working on theories of quantum gravity to fundamental issues about entanglement, and to try to look back at perhaps I think the thinking is perhaps we moved a little too quickly over these issues. We operated in this shut up and calculate mode and worked out quantum field theory, but now in trying to move to a fully quantum theory of gravity, there are new conceptual issues that we're facing. And I think it's fair to say, certainly amongst the string theory community in the last 10 years, there has been a return to these foundational questions and how it might motivate developments in string theory, for example.
I guess I'd also say that there's a problem with just going back to 1926, which is that the weirdness has to do with these interpretations. And the definition I'll take of interpretation is a different picture in your mind for something that makes precisely the same predictions. Right, and that's our problem. We have a nice mathematical formalism. It makes unambiguous predictions. What we don't know is how we should think about them. And there's no way, if you and I differ about that interpretation, that one of us can prove the other wrong, because we're making all the same experimental predictions. So to me, the question of which interpretation is true or false is either just, an unanswerable metaphysical question, one of us is right but we will never know, or it's a practical question having to do with which interpretation is more useful. It might just be we get further if we think this way than that way, or we get further on certain problems thinking this way and on certain problems thinking the other way. Or if the theory is wrong, right? If we're going to have a new theory that goes beyond quantum mechanics, it's very likely that some aspects of some interpretations will survive and others will not. So if that's what we're hoping for, to really find evidence that one interpretation is right and another is wrong, it has to come from something beyond quantum mechanics. So it's natural to ask which of these will be fruitful for pointing us to that successor theory. So to me, that's the most natural way of asking anything objective about interpretations.
From the perspective of philosopher, at least one, I find the question, which interpretation is correct, less important. I think that my interest is that quantum mechanics is like laboratory of metaphysics. You by trying, because it's so constrained, as John mentioned, it's not so easy to come with an interpretation. Whenever you try to push it, it goes in another direction and you have to go more radical. The interesting thing about it is that it pushes the philosopher. When I started, thinking about quantum non-locality, I wanted to use philosophy in order to understand it. But the process was that I had to change my philosophy because I had to think about probability differently. I had to think about causality differently, about properties, about a lot of our metaphysics are basically come from classical physics, from metaphysical intuition at least. So I think that this is, given that it's so constrained, the game, and you cannot do whatever you like, I find that different interpretations give you different metaphysical options that are interesting. And one never know what will happen. Maybe the next theory will just use one of these or to develop some new framework.
Tommy?
Yeah, there was some discussion about how different interpretations of quantum mechanics have different takes on whether it's a probabilistic or deterministic theory. My question was whether the same holds for whether we should be realists or anti-realists about quantum mechanics. Just to give an example, Professor Steinberg, you mentioned how you're a realist because of your laboratory work, like a photon retains its properties in the time interval between two measurements. But Professor Seip, you mentioned how there are some interpretations which don't let you speak very straightforwardly about measurements. It's position measurements, not measurements of position. So does that mean that if you want to be a realist, you've got to pick your interpretation very carefully?
I think if you want to be for our current understanding of interpretations of quantum mechanics, if you want to be a realist, you have to be a very strange person. You have to put up with a lot of features. However, whichever realist route you take towards it, and by realism here, I mean just asserting that the abstract elements in the theory refer to things that actually exist in the world, not just tasks in the laboratory or sensations or anything, but that actually refer to things in the world. If you're going to go down that route with at least the realist interpretations that people have developed, and there's a host of them, okay, you have to be able to accept a very, very strange universe.
I think it seems to me that there is sometimes, a kind of disposition against, that if you are not realist about your theory, there would be a problem in developing it or taking it seriously. But I don't think it's necessarily the case. I think that if you look at the history, some people were more realist about theories and some other less realist. And as I said, quantum mechanics gives a lot of options. Some of them are deterministic, some indeterministic, some realist. I think even when someone is anti-realist, I don't think that one is anti-realist about everything. It's about part. For instance, in the measurements, we go from a superposition, which is not definite properties, to a definite property. I don't think anyone takes seriously the collapse, so-called collapse in standard quantum mechanics seriously, because it happens immediately. It violates all conservation of laws and all these things. It cannot be right. Everybody knows that it cannot be right.
There are people who think that. But there are people who take it seriously.
Take it seriously. I know. Okay. So I think that
blindly happy with it.
So I think that we can be instrumentalist about this part of the theory. One need not be instrumentalist about everything in the theory and say that there is nothing in the world. I think, for instance, from my point of view, working on the Finetti, the one of the founding fathers of subjective probability, he was instrumentalist about probability, but not necessarily about event and objects. So it's different. He thought that probability is not something in the world, is something that we have as a state of expectation or judgment. But of course, there are things in the world, and he was happy, to accept what the scientists would say about it, the physicists.
So, I said I was a realist earlier, and now that people are using the word slightly differently, I want to say I don't mean that I have any special knowledge that objects have definite positions and momentum, or that the wave function itself is a real thing, or that the photon between these 2 points, a photon is a thing. What I mean when I say I'm a realist is that I believe the task of physics is to try to learn what actually exists in the world, that there is a world out there, and we're not merely trying to write equations that describe the outcomes of experiments, but we're trying insofar as possible to learn what is this stuff out there, what exactly that is, how we should best describe reality. I admit my ignorance about that. But my, quasi-religious belief is that there is an answer to that question, whether or not we ever find it.
But then what would be your criterion of success?
Can I ask the philosophers
in
to do
that program, wouldn't it be something like saying what the properties of things really are in the old-fashioned sense of the word properties?
So I think that there's some. So realism is a kind of a catch-all term for a bunch of different kind of commitments you might hold, and the space of what fits in that catch-all group just grows tremendously once you move to quantum mechanics, because there are things that you might have considered as not really realistic that now become they become what would be a full story about the world if quantum mechanics happened to be true of it or something like that. So you mentioned that your realism is effectively a denial of these kind of instrumentalist attitudes, that's kind of sufficient to get a realist view off of that, or that's one sense in which realism has been used in these debates. But there's more you can say about, or there's different kind of ways to put flesh on the bones of what realist commitment is. Namely, you might think not just that we're in search of the real stuff that there is, but in fact that the theory tells us what the real stuff is. And that's another connotation the term has taken on in these debates.
But I fear that's a kind of I know it when I see it answer. That as long as we believe Newtonian physics, we all looked at those equations and said, I know what these variables are talking about, so those must be the real things, and that was easy. And now we're in a situation where that's hard. Yeah. And maybe that's because our theory isn't good enough and we'll have one where it becomes easy again. That would be really nice. Mm-hmm. Maybe it's because the thing in our theory, this wave function psi, really is what's real, and that'll be obvious to people in 200 years, but it's weird to us today. Yeah. It seems unlikely to me, but it's possible. All right.
I think, from my point of view, I think that many times people, underestimate how instrumentalism can be sophisticated. But I do share your view that I'm not happy with instrumentalism, although I work about it because I want to know, the way, that's one of the things that attracted me to. On the other hand, it might be difficult or maybe impossible to know what, nobody, promised us a rose garden. And it's a possibility, that maybe we are not able, to find what's going on out there, but as an intellectual, curiosity, I want, to be realist. I'm not sure I can be.
I guess I'd also say we all know that there are different levels of description. There are things like sound that exist. I can't point you to sound, right? But we know that it exists as a phenomenon. And in quantum mechanics, it gets even more complicated, and in field theory, yet more. So we were skirting around this issue of whether or not a photon exists. And from a field theoretic perspective, it doesn't really make 100% sense to talk about this photon as an object, nor does it make sense to talk about this electron or this atom. And yet there are situations in which that's a reasonable way of speaking. There's a phenomenon that in certain situations, in certain limits, you can think of as having reality. And to me, that just makes it all the more difficult to answer this question objectively. How do you know when you've described reality? Most of our descriptions of reality involve different descriptions that have different regimes of validity and are approximate and work sometimes. That doesn't mean we don't believe there's something real out there, but it means we have trouble just writing down one description and saying this is what is real.
So to be realist, is not necessarily to expect that nature would be very simple and nice. Mm-hmm. So for instance, in my view, what quantum mechanics is pushing us, at least the mainstream interpretation, in which the particle could be in a superposition of being here and there but nowhere, is that, for instance, in metaphysics, traditional metaphysics, is to be somewhere. But in quantum mechanics, to be is not necessarily to be somewhere. Mm-hmm. Is to make a difference, for instance. So it pushes one, to think about metaphysical issues and to have a framework that is different. It might be strange for us, but maybe in 2 centuries it would be totally natural. Because I remember the first time I saw the superposition, I thought, this is not real. that people believe in it. But after some time, you get used to it, and this is a position, not such a big deal.
Hayden? Yeah.
This is a question, more of a clarification question than anything. You guys all kind of alluded to this word information before, but it was not really a satisfactory definition. So I was just wondering, does that definition change either conceptually or mathematically from interpretation to interpretation? And if so, how? And if it doesn't change between interpretations, then what are some common definitions for information?
Well, so I mean, in the language of engineering and mathematics, the standard definitions of information is Shannon information, right? So, which pretty much measure the statistical distributions of what is called the source of information, right? So you have that formulation which is similar to entropy, that kind of thing. And of course, people are not everybody is happy with staying at the level of Shannon information. So, I mean, in the 50s, there significant effort trying to extend the notions of information from the pretty much structural, syntactic sense to the more semantic sense, which tied information to meaning of a language or contents of messages. Well, so and there are different attempts along that direction, but so far probably the most common, the most obvious common denominator is still to take the Shannon's view as a sort of the information as a measure of the statistical distributions of the source of information. So when we talk about quantum information, there's this narrow sense of trying to extend the Shannonian information to the quantum system. So when we talk about, let's say, the transmissions of information through the quantum system, through like entanglements or EPR, then how does that change? How does that differ from like the classical information theory? So this is quantum information in the narrower sense, which has more to do with the Shannonian formulation in the context of new quantum systems. But I mean, as a linguistic and cultural phenomenon, this quantum information has been used more in a more free ways. When people are talking about, say, the quantum system that is used to deal with computation, deal with information processing, deal with communications, they talk about quantum information, which doesn't seem to have a very rigid, well-defined technical definition. But again, language is something that you cannot control in the narrow technical sense, even though I know experts want to control the use of language in a more strict definitional sense, but still it just spilled over like a lot of natural phenomena. My take.
Yeah, there are some philosophers that try to use information as the basic ontological thing. I mean, John talked about it, but they don't say what it is. And I think that they believe, I mean, or their aim is, to solve some of the interpretational problems of quantum mechanics. But I share the same feeling as John. I mean, that I don't think that they actually give us, tell us what is this notion of information that is supposed to be the basis. So they try to derive quantum mechanics from axioms about what you can do about information in the quantum worlds, which is different from the classical worlds, and to show also in what sense, quantum mechanics is different from classical. But as far as I know, they don't say enough about what the information is or what information is about, which I find a problem then. it's not that it's not an interesting exercise. I think that I learned a lot. I mean, I think people learned a lot about the theory from doing these things, but I don't think it solves the interpretational problems.
We're gonna have to do the next few kind of quicker, but sorry about that. Jack F.
Yeah, my question is kind of more about the relationship between the disciplines. If we have representatives of a couple of different disciplines, as part of the panel. And so my question is kind of, so for philosophers, how, in what sense does the physics, like the results of theory, the results of experience, affect your work as a philosopher in terms of writing and teaching and thinking? And then ditto for the physicists. So how much does kind of philosophical thinking, maybe it's guiding intuition or guiding teaching, how does that affect you or factor into your work?
Well, I'm probably a funny philosopher in some sense, in that I more frequently find myself reading physics papers than I do philosophy papers for the purposes of my research. But that's because I'm interested in these questions right at the boundary of, how a mathematically expressed theory like quantum mechanics can actually hold information about the physical world. And I don't see a way to address that kind of question that isn't overtly philosophical, but also doesn't avail itself of all of the resources that we have from our best physical theorizing. If you were to ignore that, if you were interested in this question and you were to ignore that, you'd be setting yourself up to not give the best possible story that you could give. So I view the projects as just fundamentally linked up with one another. And, it's not the kind of, I couldn't just do philosophy or I couldn't just do physics to try to address the questions that I'm interested in.
Yeah, I fully agree. I think that it's strange to do philosophy of science without trying to learn the science. I think, or to know, and I think it goes both ways. I mean, the influence. Also, history of science. I think that all the three are very important, to understand science. And it's not easy to understand. So I don't think that just by thinking philosophy, and also when we think philosophy, many times we think things that were influenced by science is just 2 centuries ago. So I think that, and my experience is that there is actually a continuity. So there are a lot of conferences in which there are philosophers and physicists, and sometimes the philosophers do more technical work, and sometimes the physicists do more, theoretical or philosophical work, and there is a kind of, so for me it's interesting.
Can we hear from a physicist? Which one of you is more likely?
Well, from the experimental side, I'll have to admit that what we do is very rarely influenced directly by work going on in philosophy now. We're interested in philosophical questions. When I decide which problems it might be interesting for us to tackle in the lab, hearing what philosophers and our more philosophically minded colleagues are interested in, the questions they're asking, helps us. But then we usually pursue them without any real knowledge of the philosophy. Right? I don't claim to have an understanding of academic philosophy. I don't read the current philosophical literature.
Go ahead, please.
Sure. Yeah. I got into having concerns about these sort of things when I first had to teach a quantum mechanics course. For the first few years I was a professor here, I was teaching things in electromagnetism and nonlinear optics and so on and so on. But then I had to teach a third-year quantum class, and I'd done well in my quantum courses in university and so on, so I wasn't afraid to try to teach it and so on. But then when I was starting to prepare the lectures, I found that none of it made any sense to me at all. And so to the extent that I know any philosophy at all, or sort of function with that language, it's because I was driven to it out of a dire state of desperation and would never otherwise have gone there.
And then Josh. Okay.
Going back a little bit more towards like the physics and getting information theory, within quantum computing, there's usually a lot of work in resource theory, doing entanglement and Discord, sort of resources that enable you to do more powerful computation. And clearly this is useful operationally, But what I was wondering is, do you think that this reframing of how we view quantum properties gives us any new insight into the metaphysics behind it?
I don't think there's too much of a connection. I mean, there are some connections. The strongest connection, maybe, that I can think of at the moment is that if you're doing, there's a lot of work now. People are interested in quantum computation with continuous variables, and you talk about things called squeeze states and using those, but you can never do anything really interesting if you only have squeeze states. You have to add something else to it. And you can sort of understand that, I guess, because a squeeze state can always be described by a positive Wigner function, which means that at least with respect to certain experiments, you can describe the results classically. So there's a little bit of a link there, but I'm not sure how really strong or rigorous that is and how far one would want to push that.
I was initially going to say that I didn't think so. I think resource theories are very powerful, the same way that thermodynamics, entropy changed the way we think about the world, but maybe not changed our metaphysics. But John's comment leads me to think of one thing that might point to an exception, which is one place we think about resources is when we ask, what does it take to build a quantum computer? And I'm going to use a narrow definition of quantum computer. I specifically mean one that we could not simulate efficiently classically, because otherwise who cares? So that's what people are looking for. And the funny thing is you say, well, what are the elements you need to build a computer? You need some logic gates. You need, and, or, and not, or something like that. And people who studied quantum computing have done the same thing. They've figured out what's the complete set of elements. If I had these elements, I could build any quantum computer I like. And there are different answers. It turns out there are different sets. But typically you look at these sets and you find, oh, that's interesting. If I only had these three elements, whatever I built, I could simulate classically. If I only had these two elements, whatever I built, I could simulate classically. But you put them all together, and suddenly I can't anymore. And as we learn about these different sets, what are the minimal resources required to do something that you fundamentally couldn't do classically? I could imagine that that's teaching us more about what really makes quantum mechanics so difficult. So different. If you ask people today, experts in the field, what is the feature of quantum mechanics that allows you to do things more efficiently than you can on a classical computer? They can't give you a uniform answer. There are simple answers people like to give, but there are people who tell you they're all oversimplified. And it does seem to me that if we understood those resources, we'd be narrowing the bullseye down on what is it that makes quantum mechanics more powerful. That might teach us something about the metaphysics.
Well, that's the end of the question list. And pretty much, I'm sure everyone's dying to escape this. Oh, sorry, yeah. Yeah.
Professor Steinberg and Professor Berkovitz talked about the deterministic and the probabilistic theories. So my question is it possible that history is probabilistic? So we have no idea what happened in the history and I can write a wave function to predict the history.
Do you want to take that? That's a great question. The arrow of time is another very deep philosophical question that we haven't touched on here. I would say that if you only specify our knowledge of the current state of the universe, then quantum mechanics leaves the future and the past equally uncertain or equally certain, depending on which read you take. So certainly the traditional way of describing quantum mechanics is to say, if I didn't measure which slit a photon took through a double slit apparatus, but I see it land somewhere on the screen now, I cannot talk about which slit it went through. It really went through both. And that's exactly analogous to saying, if I fire a photon out of a laser now, I don't know which slit it's going to go through in the future. I think those two things are uncertain or certain in exactly the same way from the perspective of quantum mechanics. And all of the same issues that arise in regard to the arrow of time classically, they remain to be addressed here as well.
So some guy can write a Schrodinger equation and the time.
Exactly. The equation is completely time reversible. So it can be used just as effectively to retrodict the past as it can to predict the future.
Then can I say that history is whatever? We just don't know history.
The standard take would say that you have to say that there are things in the past that are uncertain in exactly the same way that there are things in the future that are uncertain.
My second question is about human consciousness. So we discussed about that in Professor Berkovitz's philosophy class, and my question is, say I'm doing a quantum mechanical experiment and a mosquito flies over the system and sees the result and the system collapses.
Can you repeat the question again?
So I take it the thought is there something specific about human consciousness in particular, as opposed to the consciousness of what we take to be some lower level species?
It's also about consciousness about insects and other animals. So if a mosquito flies over the experiment and sees the result, then does it also cause a collapse?
Yeah.
So this is one of the troubles with trying to take seriously theories where there is some fundamental role for a conscious observer in producing the collapse of the wave function. Namely, we don't have a good handle on what we mean by consciousness, or I take it that's the received wisdom. And so if you want to use that as a way out of the measurement problem, then you need to say something about what kinds of conscious beings are sufficient to actually induce wave function collapses. So, and I think there was moments in history where this question was seriously debated about, like whether or not a dog could collapse the wave function, or whether or not Schrodinger's cat itself could collapse the wave function. I don't know. It strikes me as a problematic direction to move as a way out.
But to come back to this thing I tried to say earlier, but probably wasn't very clear about, if you had a system like a mosquito that was capable of garnering information about the behavior of a system, which slit a particle went through, or something like that, that would have experimental consequences on the system itself. And it is completely irrelevant whether the mosquito is conscious or some microscopic system or some macroscopic system. We know what that would do experimentally to the rest of the system. And we don't need to make any assumption about collapse to make those predictions. And that's why I say the second bit about claiming that at some point the state gets replaced by probabilities, that there's an observation, that's the only tricky point, and there's no experimental evidence one way or another about how to think about that.
I agree. I mean, with what Mike said, that I think consciousness many times is a way to try to solve the problem that cannot be solved otherwise. It's not that consciousness is not important, but I think that these solutions are problematic. As for probability and determinism, I think that it shouldn't. I mean, we shouldn't actually talk about determinism versus probability, because probability pertains both to determinism and indeterminism. And actually the inability to predict, it may be in some way much worse in chaos theory that is deterministic. So it's not, there are different kinds of uncertainties, that we have in terms of predictions, and one can talk about them in probabilistic terms, but I'm not sure that deterministic versus indeterministic, they have different, they present different challenges, but it's not that only one way. That if you have deterministic theory, you can predict. Because even if things go deterministically, we know from chaos theory that it's extremely difficult. And systems that are very chaotic, it's hopeless to try to predict. What do we do?
I think it's better leave that here. If you want to ask questions, maybe you can ask afterwards. I feel like we're now getting very hot and reaching the end of the time that we're allowed to be in the room. So I just wanted to express my thanks to you guys for agreeing to come out and talk to us, and it was a really interesting conversation. and I'm sure a lot of it went over my head, but I did get a lot from it, so thank you very much. And we have some very small tokens of our gratitude to give to you. Perhaps I'll give them to you afterwards, though, just to not interrupt this situation so people can escape. I also want to say thank you for you guys putting up with the heat and for asking lots of interesting questions and being engaged. And also to let you know that, yeah, we will be heading to the pub after this, probably a bit later than originally anticipated, but please feel free to join us, and we'll probably be buying a round or two on ASU, so do that. And then also we'll also be having another event in January, which will be a social event, so probably less, I guess, informative as this one. However, it will be fun, and we'll also be having another academic event that you'll probably hear about on Facebook. So yeah, keep your eyes peeled for that. And yeah, you may escape.
Thanks for organizing.
Thank you for all.
Thanks.
Thank you.